So it's a great pleasure to return to Daejeon and give a presentation, to KAIST students. Okay, so today I'm going to talk about transformative architecture, enabling technology for next generation structures. Okay, so first, before I start, as Professor Chang mentioned, I was working at the University of Washington in the last 10 years. So most results that I present today will be based on my former work. Okay. So what is transformative architecture, right? So then it's basically architecture that is changing its shape. So one good example can be aerospace structure. This is solar sail. So when it's being launched, it should be in compact shape, and in the space, it should be deployed, right? And also in the civil infrastructure, we also have this type of, you know, uh, inflatable structures, which can be also transformative architecture. Like biomedical engineering, stent is a device that needs to be positioned in the right place. Then it should be expanded, right? So stent is also structure that is changing shape. And this is kayak, which is actually you can purchase this in Amazon. Can anyone guess how much this is going to cost? If you don't have this deployable kayak, then typically people carry very bulky, heavy kayak on the roof of your car. So it's pretty difficult to mount and also unload it. Okay, but this is something that you can carry fairly easily, right? I mean, you can basically make it into small bag. So how much would it cost? Can anyone guess? $1,000. Very good. Yeah. So this is one passenger kayak, which is about $500. For two passenger one, it's about $1,000. Okay. But if you think about raw material cost, it's going to be much lower, right? But at the same time, kayak, you have to make sure that there is no water leakage, right? So how are you going to make it foldable without creating any leaking points, right? So that's pretty challenging task. Also, I mean, investigation on shape changing can be also a subject of, for example, protein engineering. How protein is being folded, that's also something that shape changing can be also an important topic. Likewise, in computer science discipline, people work on shape changing a lot. Okay. All right. So in this presentation, I will briefly touch on three different topics. The first topic is chiral transformative architecture, which will be used for efficient impact mitigation. Second topic will be extremely anisotropic and tunable architecture, which can be used for designing lightweight, deployable, yet load-bearing structures. Last one will be topological insulator inspired architecture, which will be used for efficient vibration field shielding. Okay, but all these topics are based on the on-demand shape design. Okay, which will be connected to the on-demand function changes. All right. So for that, I'm going to use different disciplines, for example, nonlinear dynamics, mechanics, etc. All right. So first topic will be about this structure, which I'm going to leverage nonlinear dynamics. Okay. All right. So impact mitigation is a very important subject in aerospace engineering and also in different engineering fields. This is a video of Falcon 9 in SpaceX. So SpaceX Falcon 9 is known for reusable rocket motor. It can be used again and again, But when this is being landed, we have to make sure that this structure is safely guarded, I mean, otherwise this can be catastrophic, right? So when it's landing, we have to make sure that this is safe, okay? So if you think about typical landing structure, when this structure is touching the ground, there will be large amount of impact applied at the bottom, right? So people typically do use, for example, this type of metallic foam. So metallic foam is inserted here so that when impact comes in, then we minimize the energy transmitted to the main body. This is typical approach. But using transformative architecture, especially also leveraging nonlinear wave dynamics, I'm wondering if we can convert this impact into tension, okay? So that means if this structure is landing on the ground, instead of compression transmitted to the main body, it will be tension. Can you picture that? Well, what would happen? For instance, if you're wearing a helmet with this type of capabilities, then something hits on the surface of helmet, instead of inner part of the helmet pressing your skin, it will basically pull your skin, right? That means you're not gonna feel any impact. So this conversion of compression to tension, is it possible? It sounds a bit counterintuitive, right? I mean, can it really happen? So I'm gonna explain the prototyping process and the actual phenomena. Then I will return to the physics behind it, okay? So for this purpose, I used chiral transformative architecture. So this is like origami structure, which is under the compression, it has coupled motion of compression and twisting, okay? So this type of, pattern can be easily found. For example, when you have a very thin-walled cylindrical structure, if you are buckling it, then you have basically triangular shapes on the surface. But if you are compressing at the same time twisting it, then you have this type of chiral architecture, okay? So this is called Kressling pattern. So analysis on this can be a bit complicated, which you can look up, references including this, but in this presentation, I will just talk about the phenomena, okay? So to fabricate this, we use a laser cutter, and we basically fabricate single unit cell, which is elastic, right? Under compression, it has also rotational motion, okay? So what we do is we connect it into this single chain. We have 20 cells, okay? And on the left-hand side of the structure, we have a very strong vibration shaker. We apply high voltage signal, and it is basically applying strong impulse to this system. And we have 6 GoPro cameras. So if we have 2 cameras looking at one object, then we can take 3-dimensional coordinate of the object, right? So each pair is measuring dynamics of 1/3 of the structure. And these balls are basically for keeping track of the motion of this structure, okay? All right, so this is a result. We are applying impact from the left-hand side, okay? So please watch carefully what's happening. So red arrows represent motion towards the right. Blue arrows represent motion towards the left. Any elastic part, structure under the deformation, it tends to bounce back, right? So it's compressed at the beginning, but it tends to bounce back. That's why we have these blue arrows generated. All right, but interestingly, red arrows are disappearing very quickly, but blue arrows are transmitted in a more robust way. Okay? So this is animation based on experiments. This is not just simulation, but this is experimental results, okay? So what's happening is, again, red color is compression. When the impact comes in, this is compressed, so impulse is transmitted, but again, due to the reaction, we have blue color following. But what happens is, the speed of blue color is faster than the red color. So at the end of structure, please watch carefully which color arrives first. Is it red or blue? It's predominantly blue color, right? That means even if you have applied impact on the left-hand side, what you feel from the right-hand side is not the compression, but the tension. All right? So what's happening there? So this is experimental result, time and space. The first cell is experiencing very strong impulse, which is compression, okay? Then due to the reaction, we have a negative dip, which is, again, reaction, okay? But this system is dispersing red color, compressive waves in the space and time domain. But the blue color is propagating very robust way. So at the end of structure, you feel blue, not the red, all right? So this is so-called rarefaction solitary waves. And this is based on the overtaking of this blue color wave over this red one, right? So at the beginning of the presentation, I said I'm going to convert compression to tension, but what's happening is actually compression is still there, but make it dispersed, make it spread it over. But the blue color is we are going to make blue color propagate robustly, okay? So the physics is fairly simple, okay? So let me explain this using very simple explanation, okay? So under the compression of this single unit cell, we have force displacement curve, but this is not linear. It's basically nonlinear, right? So force displacement curve, the slope is representing stiffness of the structure, right? So at the beginning of the compression, it's fairly difficult to compress, but as you compress more and more, slope goes down and down. So it gets softer and softer. So this is not linear, but this is nonlinear material, okay? So what happens is, typically stiff material tends to propagate waves faster, right? Soft material has slower wave propagation speed, right? So if you have this type of impulse with the low amplitude and high amplitude part is having low slope, which means propagating slow. Low magnitude part is having high slope, which is making waves propagate faster. So as it propagates along the chain, the system gets basically, wave gets dispersed. So this is efficient way to disperse waves. But if you think about the other domain, which is tension, this is the opposite, right? At the beginning, which is low tension, this is low stiffness. But if you have higher tension, stiffness goes up, which is making this wave propagate faster. This is helping the waves to build up to create shock type of wave, nonlinear waves. Okay, so this is basically helping wave localization. And this happens a lot in fluids, actually. In fluids, you see nonlinear waves, right? I mean, this is solitary waves, like single pulsar wave propagating very robustly. But you also have, for example, tsunami type of waves, right? So in fluids, this happens a lot because fluids is nonlinear, but typically solids, we have only stress strain curve in a very small domain. Typically, Young's modulus is good enough to explain most of the wave phenomena, right? But this is origami. We are basically leveraging the full domain of strain, which is nonlinear. So that way we can basically leverage nonlinearity of the structure. Just like nonlinearity is used to create nonlinear waves in fluids, this is structure, but we can still create nonlinear waves because of this soft nature, okay? So we can also derive equations, and which is very similar to classical wave theory equations, so-called KdV equation, okay? All right. All right, so this is KdV solution. So this is basically what did we do with the transformative architecture as a first part. We used it, to enable soft structure. In that soft structure, we created nonlinear waves, okay? So that was our first part. Of course, we wanted to do more than just a simple paper-based origami system. So that's why we built this composite origami. Typically, composite is not good material. It's not a good material to be used in a typical automotive structure because it's too brittle. When it's being impacted, it shatters around like glasses. Okay. Also, it's very expensive to fabricate composites. So, but this way, by making composites in origami way, we can make it pseudo-ductile, which means when this is under impact, the structure is collapsed layer by layer. So it can absorb a lot of energy. Okay. Second, we can also use filament winding, which makes it less expensive to fabricate this. Okay. So this is video clip that shows impact of origami. As you see that the structure is collapsed layer by layer, right? So this way energy absorption can be improved. All right, that was my first part of the talk. So just summarizing that, I've shown rarefaction waves, and also likewise, we can also make waves turn around like boomerang. You impact on one side, not even before reaching on the end of the structure, we can make it turn around. That's also by using nonlinear structures and the nonlinear wave dynamics. We can also make a 3D printed lattices, and this also enables you to create many different types of waves, okay? All right, so let me move on to the second part, which is an isotropic and tunable architecture for making lightweight, deployable, yet load-bearing structure. So I said three different properties, right? Lightweight, deployable, yet load-bearing. Typically, to make lightweight and deployable structures, the structure needs to be very compliant, very easy to be, folded, right? But if this structure to be load-bearing, the structure needs to be stiff, right? So we are talking about two different contradicting properties, all right? So, but this is important in many cases. For example, when you have disaster relief structures, typically this structure needs to be stored. Stored in a compact manner. Under the disaster situation, it needs to be deployed, right? So this type of structure needs to fulfill these properties. Likewise, when you build space habitat, you launch the structure in a compact manner, and in different planet or elsewhere, it needs to be deployed, right? After deployment, structure needs to be stiff and strong, right? Likewise, in your daily lives, packing materials like this, it needs to be actually make it folded, right? It needs to be stored in a compact manner. At the same time, these boxes need to protect materials inside, right? Items inside. So there are many cases that you have to fulfill all these cases, okay? All right, so how can we do that? We are proposing origami, particularly something called Tachimura polyhedron, okay? So this is just a combination of two different sheets of papers, all right? But you basically have this structure has different Poisson ratios, different stability, different stiffness, a lot of different properties that you can actually tailor. So I'm not gonna get into detail, but mechanics of origami, this is very interesting part of the mechanics subject. Just one case, I can make this into tessellation, which means multiple cell structure. And you see that this is, easily compressed. But at certain direction, it can take the load. But even that certain direction, I'll show you what happens, okay? All right, this can take the load, but if you make it slightly change initial condition, then this structure can be collapsible. Okay, so what happens is basically, let me play the video. All right, so one structure is easily collapsible, the other structure is load bearing. But I'm talking about the same structure, okay? But depending on its initial condition, whether this is concave or convex, one structure can be collapsible, the other can be load bearing. And in terms of the, force displacement behavior, it's quite different, right? And when we measure force that this structure can handle, it can be very low when this is this configuration, but when this structure is converted to the other configuration, the load that it can carry is very high. Very simple principle, right? But by using this, we can make the structure easily foldable. At the same time, it can take the load, all right? Nothing complicated. So using that, we can build disaster relief structure like this. At the same time, this is a structure based on Tachimura polyhedron. We can potentially make this into space habitat or different architecture, okay? All right. And what else? Again, this can be made into tessellation. This one has many different properties that you can dial in, you can tailor. Depending on what you need, you can have specific Poisson ratio, specific density, specific stability that you want, all right? So origami gives you a lot of design freedom, okay? Another interesting property is this structure can be reconfigurable. The whole structure can be made into many different shapes. So for example, 3x3 cells, we can make it into many different geometry. If you have 7x7 cells, it enables you to achieve about 1,000,000 cases, okay? But it's interesting how you can actually calculate, all those cases. This is computationally a very interesting problem. So we have used graph theory, which is a tool that, many different fields use, including mathematics and computer science. But using this technology, we can calculate how many cases are possible using this tessellation, okay? All right, so another way that we can leverage this is 3x3 cell structure, which can be converted to many different geometry. This is only showing 4 different cases, but each case has different geometry, right? For example, this one has 9 square shapes. This one has, for example, 6 square shapes and 3 rectangular shapes. So depending on that, this structure will have different stiffness when this is being compressed from the top. So that enables you to have different stiffness. So which means this origami system can give you variable stiffness system. Likewise, the entropy of this structure also changes. Okay. And back to the application. This is where you embed a raw egg inside of this cell. This one is the second case. I mean, typically when you order things, for example, Amazon or Coupang, this is how it is, right? We have a lot of packets, but it's out of focus, but this egg is broken. The other case, egg is not broken. Okay. So one interesting case. But interestingly, one of my students proposed this in the AIAA conference, and she won the first place award by using this origami-based impact mitigating structure. Okay. All right. So just summarizing what I've presented in the second part, origami can give you interesting design tool that enables you to change material properties. In this case, Poisson's ratio, density, and modulus. Okay. And we can build it into prototype, and this is another example, dodecahedron, which can be actually deployed into this interesting polyhedron. I'm going to talk about this a little bit more at the end of the presentation, but again, this is an interesting design tool that you can use. All right, so let me move to the last part, which is topological insulator. How many of you guys heard of topological insulator? 위상절연체. This has been not much explored in engineering, but in the realm of physics, this was a really hot keyword. In 2016, 3 scholars won Nobel Physics Prize based on topological insulator. So what am I going to do with that? Okay. So if you think about aircraft structure, noise is a big issue, right? It's really bothering. Another issue is the noise between floors, right? 층간소음 문제. Okay. Is there any way that we can fundamentally tackle this type of problem? Typical structure, when there is noise source, waves propagate everywhere. But if you have a new type of structure with source of noise on the surface, what if the structure doesn't allow waves to penetrate inside? Then you can actually have a very quiet aircraft. You can have basically complete shielding of noise between floors, right? So that is possible if we borrow a concept of topological insulator, okay? So that breakthrough happened in condensed matter physics, all right? So topological insulator is a material which is insulating inside, conducting outside. So what do I mean by that? Typically, you think about insulator, material like rubber, right? It doesn't allow electrons to travel. If you think about conductor, you think about metal, right? It has free electrons travel everywhere, right? But topological insulator is insulating inside, conducting outside. It's like chocolate. Chocolate inside is insulator, outside is conducting, right? But this is, of course, made of 2 different materials. But topological insulator is a single material, uniform material, which is only allowing electrons to travel outside. So again, this one led to the Nobel Physics Prize for these 3 scholars. So original topological insulator concept came from the condensed matter physics. So this is 3-dimensional structure, but electrons only propagate and travel outside of structure, which has been realized in photonics as well. Only light wave propagate outside of structure. Also in acoustics, this is 3D printed lattice. If there is sound created one part of the structure, sound only travels outside. But there hasn't been much work on the stress waves. Okay. All right. So that's the part that I would like to address. So this is a lattice that my team has built, simulated. This structure actually enables wave propagate only on the surface. All right. This is made of this type of lattice. A lot of lattice that we have used. But as you see here, As you see here, waves don't actually get inside of the structure, okay? So if you, like this is highlighted like waves. Waves only propagate outside. Even if there's defect, there is no backscattering, but waves only travel around the structure, all right? So if this is possible, again, as I mentioned to you, a lot of applications, automotive vehicles, there is noise outside, then we can make sure that noise doesn't get into the cabin. And I mean, this high precision electronic equipment, vibrations coming from outside, we can actually isolate it, right? So the question is, okay, so this is a 3D case, but my team started with a lower dimension. So this is 3D structure with only surface waves, which is 2D waves on the surface. Similar concept is basically 2D structure, which is plate structure, and only we guide waves in just along the line, which is 1D, okay? So this topological waves is basically lowering energy dimension 1 down, okay? So but if you think about typical waves in 2D structure, if you have, for example, wave source here, waves propagate everywhere. This type of wave propagation along the certain waveguide is very difficult to achieve. Okay, so if we can guide waves in this specific manner, then we can have new paradigm in energy harvesting, sensing, and actuation. So what we have done is basically a couple of students worked on mounting bolts on the plate. All right. So I will show you how we fabricate, and I will show the physics. The physical phenomena later. So, how many bolts do you think these students have mounted? 몇 개 한 것 같아요, 학생들이. If you are graduate students, you have to have good sense, because if your advisor asks you do this, you have to say yes or no depending on, how you think how much work and time you are gonna need to do this. 몇 개 필요할 것 같아요, 몇 개 볼트? Thousand. Who said thousand? You have very good sense. How long would it take? How long would it take to mount these 1,000 bolts? Your answer is pretty correct. 1,300 bolts. So how long did it take? Two students basically worked together, right? A week. Who said 1 week? Very good, very good. So at first they mounted all the bolts, but the bolts were actually rattling. They were not firmly mounted. So they actually removed all the bolts. And if I play one more time, you will see that they are actually, one student is drilling the bolt and one student is dropping a super glue to make sure the bolt is firmly attached to the plate. It took them whole week, yeah. So they said they're not gonna do this, make another plate, but later you'll see they actually created another plate, but I will show you later, okay? But anyway, what does this structure do, we built this type of structure. This is looking at the back side of the structure, okay? You see, one side, this purple regime, we have these bolts mounted in a compact manner. This yellow part mounted in the more like sparse manner, okay? So we created domain boundary. And we had piezoelectric actuator, which is pumping energy. And we used laser Doppler vibrometer to measure the subtle vibration of the plates, okay? So we excited plate measured 1 point, and excited plate measured another point. So we measured all those points one by one and reconstructed the energy, the wave propagation. If there were no bolts and we only had piezoelectric actuator, waves will be propagating all around, right? Just like you throw a stone in the quiet pond, right? But what happens by using this bolted plates? You see, piezoelectric actuator is pumping energy, and we are visualizing the velocity of the plates, okay? Interestingly, the waves propagate only along this domain boundary. Another interesting thing is there is spin. Spin. Electrons have spin, right? Electrons have spin nature, so that electrons can actually propagate along certain path. We call it spin-hole phenomena, right? Quantum spin-hole phenomena. But this one is actually stress waves. We don't have spin, right? sound waves, we don't have spin, but we were able to actually create this type of pseudo spin effect. So I'm not gonna get into much detail in physics, but for those who are interested, I'll be happy to provide you with some references. But this is again a new phenomenon based on topological insulator. Before the topological insulator received spotlight, people really didn't know how to guide the waves by using this type of display. But now we can create domain boundary. We can make the waves propagate more like very interesting manner. Also, you will see that even if we have sharp corner, there's no reflection, no backscattering of the waves. Just like pipeline, waves propagate along this path, even this sharp corner, very smoothly. So this is a new way of letting waves propagate in structures. Okay. All right. So again, this is quantum spin Hall effect. All right. So that I've just shown is 1D wave in 2D structure. But this topological insulator concept is actually even more, which is you can make the waves localized in one spot, which is 0D, right? 2D structure, 1D wave, this is 0D wave. Zero-dimensional wave is just one point in a structure. Can we make waves just be focused in one point in a structure? Can you do that? This is another plate that my students have fabricated. It's different from what you saw before, but not as many bolts as before. This is 800 bolts or something. But this is interesting because this structure always makes waves be focused at the middle of the structure. Even if you, for example, you excite the structure away from the center, at the end, waves just migrate to this point. So this is experimental result. We had piezoelectric actuator. We injected waves away from the center, but after we turned the piezoelectric actuator off, the wave actually moved to this point. So this is also something that we didn't see before. If you have, for example, energy harvesting structure, which is, vibration is all around, right? But you cannot really attach transducer all around, right? So if you have transducer attached at a certain point, then let the waves all come to that point. Then we can harvest that energy very efficiently, right? So this is one way that we can use this type of structure. So again, the first example that I've shown you is guiding waves in 1D manner. But another way is we can also, I haven't introduced this, but we can also let this wave choose one corner over the other. And last example that I've shown is in the plate, even if there is excitation away, we can make the energy focused at a certain point, okay? So this is my last part, which is about topological manipulation of energy in solids and structures, okay? All right, so let me wrap up my talk. So I proposed a structure so-called transformative architecture, which is which is a bit different from conventional structures that we deal with in engineering. First structure was about impact mitigation, converting compression to tension. Second structure is to build lightweight, deployable yet load-bearing structures. Last part was shielding vibrations and doing efficient energy harvesting, okay? So for that, I used nonlinear wave dynamics, mechanics, mechanical design, manufacturing, also condensed matter physics, okay? So many interesting disciplines that you can use for structural engineering, okay? Now that I am in this 조천식 교통대학원, I can also propose the usage of such structures for mobility. Can we use such type of structures for noise absorption structures? Even if there is noise and vibration outside, we can make quiet structure by using such structures for the cabin, for the frame of the structure. Likewise, landing of the structure. UAM, big issue is how to ensure safety of the passengers. People don't want to take the risk of riding UAM because what if it crashes? You know? So safety is a very crucial issue for this type of structure. But recalling my first topic, which is converting compression to tension, we may have very safe structures. Even if there is hard crashy landing, this compression can be converted to tension. We can safely make the structure lend even under the very urgent situations, okay? Likewise, we can also make structure foldable, reconfigurable, make a UAM structures more like, in a compact manner. Wing can be folded, other structures can be folded. Also, I haven't really introduced in this presentation, but we can also come up with many interesting robotic algorithms, robotic mechanisms by using this transformative architecture, okay? All right. Let me finish my talk with one animation that my students has actually created. So this is a dodecahedron-based space habitat, and you will see that it's looking flat at the beginning, but it can be actually unfolded into this stable habitat structure. Okay, so this is also another vision of mobility research, right? How do we actually move such type of structures to the space elsewhere, make it deployed to form very stable structures, right? Okay, so with this, let me finish my talk. And again, I worked on these research topics with my collaborators, and also especially the bolded ones are my former students and postdocs. So many work have been contributed by my collaborators and my former team members. And with this, I would like to open the floor for questions. Thank you for your attention. Thank you.
Thank you, Professor. Thank you, Professor, for your amazing presentation. I just have one question for uh the the topology insulator. Is there a certain type of frequency that absorbs or makes the acoustic wave spins, or is it applicable to all the frequencies?
So the question is for the topological insulator,
Yeah,
is this frequency dependent phenomena, right?
yeah. Basically, yeah.
That's actually a very good question. So indeed, this mechanism is happening in the so-called Dirac cone in the frequency domain. So when it's opening up, then there is actually this edge state that we can actually leverage this topological phenomena. So the answer is yes, this is frequency dependent. So there are a lot of efforts to widen the frequency ranges so that this mechanism happens over many different frequency regimes, but definitely it's limited for now. Yeah. So that's a very good question. Yeah. You can ask in Korean, then yeah, I mean I can also address your questions.
Oh, yes. We have various background actually.
Okay.
The background is especially the electric engineers.
Okay,
We don't have
okay.
any solid the theoretical background on the wave
I see.
positions and other vibrations and others. But
Okay.
he has good intuition.
Yeah. Actually, that's very good because I mean, I recently visited a company which is developing automotive components, and they were actually more focused on investigating electromagnetic kind of issues of automotive parts instead of mechanical parts. So I think working on mobility research topics from the electrical engineering background, that's very good approach actually. Yes.
저는 한국어로
네.
좀 그 첫 번째 연구 말씀해 주실 때 결국에는 컴프레션이 전파되는 속도가 느리고 텐션이 빨라가지고 마지막에 이제 그 현상을 말씀해 주셨는데 그 로켓처럼 긴 스트럭처에는 해당이 되는데 좀 짧은 스트럭처에 대해서는 적용이 안 되지 않을까라는 생각을 해봤습니다.
좋은 질문입니다. 여러분 이거 다 슬라이드 예전 이거 이미 보고 이제 질문 준비해 온 거 아니에요 혹시? 너무 좋은 질문입니다. So the question is, so the mechanism of rarefaction wave generation, is it only possible for structure with the number of unit cells, right? So the Answer is no. Because even if you see, for example, only cell number 3 or 4, you already have, let's say if you cut it here, right? You already have drastic reduction of the compression already. And then you have this tension already created, right? So even with a very small number of cells, you can achieve it. And there has been also follow-up work from different research group based on this one. They explored even shorter chain, and even within first few cells, you do have this significant effect. So yeah, we don't need many cells. Very good question.
그럼 실험을 하시기 전에
네.
이런 현상을 다 약간 어느 정도 예측을 하고 하셨는지.
So the question is, did we predict this before we started this research, right? No, I think I started this wave dynamics research in origami because one of my graduate students was Japanese and his hobby was origami. So we started working on wave dynamics in origami, but we didn't really anticipate, seeing this type of interesting wave dynamics. So, but that inspiration actually came from our collaborators. So we work a lot with applied mathematicians. So mathematicians basically said, oh, this could be a good platform to observe this type of rarefaction waves. Because rarefaction waves are not new. It's new in the solids and structures, but in different medium, in liquid, in gas, they already know rarefaction waves, right? So mathematicians have been working on modeling that, So they were suggesting, oh, this can be something that we can do, in this setting. So that's how we started working on this. So that's another, key, important message. Collaboration is very important, especially across different disciplines. And you can always get new perspectives. Okay, very good.
Thank you.
Yeah. 다른 질문들 있으십니까?
좋은 강의 감사드립니다. 이게 궁금한 점이 결국 오리가미 쪽으로 궁금한 점이 있는데 이게 뭐 차량 사고 같은 이제 단발성 사고 같은 경우에는 이제 그게 한번 이게 적용되는 데는 문제가 없을 것 같은데 뭐 힌지 부분에 이제 퍼티그가 쌓이지 않는다는 등. 근데 이런 오리가미 스트럭처가 반복돼서 사용되는 경우에 이제 사용되면은 이 힌지 부분에 퍼티가 분명히 쌓일 것 같은데 이런 프랙티컬한 문제들이 발생할 것 같다고 예상이 되는데 혹시 어떻게 해결이 되나요?
That's another very good question. So the question is, for the first structure, how are we going to deal with issues of fatigues, right? Okay, so let's see. Okay, so typically origami is we need to have crisp patterns, right? Basically folded lines, right? So to have a easy folding, we created this slits, right? But if you look at this carefully, then we have two slits. So typically when this is being bent, there is excessive stresses developed due to the bending. But by having these two lines of slits, what happens is these lines are actually being twisted instead of being bent. So we can reduce stresses quite a lot. So before we do this testing, we did a cyclic loading test. So we repeated testing unit cell loading, unloading like hundreds of times. So we have to make sure that hysteresis is minimal. And every time we do the testing, we have to ensure repetitive results, right? So if it's not, then, first time you do the testing, you have a one wave shape. If you do the testing next, then you have different wave shape, then it's not good, right? So we conducted that cyclic testing to ensure this is giving us repetitive results. But when it comes to, for example, making this into more rugged materials, we have to come up with maybe different solutions. So that's what my current team is working on. We have a plastic version of this, which is working pretty well. Well, what if we make it using, for example, composites or using metals, right? So that's a different issue. So that's another very good question.
if you have no more questions, then thank you again for your executive presentation, and please give a feedback to